Good morning, folks, and welcome to exciting Tuesday morning here at the SMPTE 2019 Annual Technical Conference. My name is Thomas Edwards. I'm with Disney. I also serve as chair of the 32NF60 Working Group on Video over IP. So this is a subject that's really close to my heart, SMPTE ST 2110, making it real. It wasn't that long ago when at a certain SMPTE technical conference, I mentioned maybe we could send our broadcast production video over IP, and people said, no, it'll never happen. We'll never send it over Ethernet, completely won't work. And I think these presentations will show that the industry has moved dramatically towards IP, especially for larger installations to try to get some of the benefits of the density and flexibility that IP can provide. We've got some great speakers here today. So I would like to begin with a paper called Strategies for Securing SMPTE 2059-2 PTP Networks. Seeing as how we're going to be doing all this stuff over IP, we may actually want to secure our network so we didn't get ourselves hacked and taken off the air. Presenters are Nicholas Caro from Oregano Systems. Nicholas holds a master's degree in communication engineering with distinction from the Vienna University of Technology. He led the ASIC design division at the university's Institute for Industrial Electronics, with research activities centered on distributed systems design and highly accurate and fault-tolerant clock synchronization. In 2001, he co-founded Oregano Systems Design and Consulting Limited as a university spinoff. He's an active member of the IEEE 1588 Standardization Committee and SMPTE 32NF Standards Group, and holds frequent seminars on clock synchronization both for industry and academia. And Nicholas Caro will be joined by Thomas Kernan, who's a staff architect at Mellanox. His main area of focus is defining architectures for transforming the broadcast industry to an all IP infrastructure. He serves as chair of SMPTE's 32NF committee and is a member of the IEEE Communications and Broadcast Societies. You may not know that Thomas was editor of DVB-TS 101-154, a specification of the use of audio and video coding in broadcasting applications based on the MPEG transport stream. And prior to joining Mellanox, he spent over 20 years in the IP industry, including driving Cisco's entry into live media production. So please, gentlemen, come up and let's secure 2059.
Thanks. Good morning, everyone, and thank you for being here bright and early. So yes, as Thomas has just pointed out, strategies for securing ST 2059-2 PTP networks. We're in the real world now. PTP has been something that's been discussed in SMPTE for a number of years, and we're now taking it one step further in the making it real. It's not about how do you deploy it, it's now onto how do you secure it. So let's start with the basics. PTP, timing, networks, and security. So obviously, the reason we need this is we need an accurate common time that is crucial for all IP studios. The problem, it's also very tempting to have this common timing model, so tampering with time transfer is an appealing denial of service vector, attack vector. PTP does provide full tolerance and resilience against attacks, but it is limited to some extent. It's not all designed within the protocol itself. The All IP Studio relies on a common reference time that is usually derived from the global navigation satellite system, so GPS, GLONASS, Galileo, or another system. And you need to keep into account that you need to model the fact that there can be internal and external threats against your infrastructure. It's all about probability, it's all about impact, and it's all about the countermeasures you need to put into place. The truth is, it's not about if it's going to happen, it's purely about when is it going to happen. You can take the if out of the equation. At one point in time, something will go wrong. It's part of the life cycle. It may be malicious, but it may also be inadvertent due to misconfiguration. So first things first, before we discuss PTP and any of the details, secure your network. If you don't do what is on this slide, or may I say it differently, we strongly suggest that you follow what is on this slide, because until the network itself is secured, there is no point on discussing securing PTP. The use of authentication, authorization, and accounting known as AAA, is the basis of who can log in, when did they log in, why did they log in, and the trail of what they did. This is key in any IT infrastructure, and it applies exactly the same in this environment. There are a number of protocols you can use for this, TACAX, Radius, Diameter, for example. The next thing, of course, is you need to secure all interfaces, and by there I mean every single possible means to access the individual hosts or network devices. Access lists is common. You want to limit the connections from authorized ranges. The whole world, even within your infrastructure, should not have access. It's usually from administrative management infrastructure that you want to be able to reach these devices in terms of being able to configure and manage them. You want to use only modern ciphers for the transport layers. This has to be encrypted. Remove the backward compatibilities, because that's yet another backdoor into your system. And you want to apply it across every single interface, as I said. Not only the web interface, but also you'll be using most likely SSH, preferably, and not Telnet. If you're using still SNMP, make sure you use version 3, which allows you to have encryption. If you have console access to the device or an auxiliary interface, same thing. You want to make sure that those interfaces are not left wide open. Someone who can directly connect into a device, that's another vector to get into your system. And whilst you may only be using IPv4, your device might come with IPv6. If that is the case, turn it off, or if you can't turn it off, filter, contain it. Preferably disable and remove anything that you're not using on a single device. This is the 101 of network security, host security. So far, nothing to do with PTP, just general network hygiene. The last point is about threat modeling. You need to understand, with the infrastructure you put in place, what can be attacked and how, through misconfiguration, through malicious intent. So you need to define how you're going to do it, you as a user or you as a vendor, per product or for your entire network. The next thing, of course, is we're using GNSS, so the Global Navigation Satellite System, and you need to be able to rely on multiple sources, ideally. So source and frequency diversity is extremely important. Many of the modern Grandmaster implementations allow you to use multiple GNSS systems in parallel, not only from different satellite constellations, but also from different bands and frequencies. You can also have supplementary information. So SBAS is another means of providing additional information for increasing the accuracy and reliability of the information that is being transmitted by GNSS for your primary reference clock. Those signals, those RF signals, also need to be filtered. There is no reason that you should be receiving energy from a satellite system coming from a non-azimuth aligned orientation. So anything that's coming from, say, ground level or from a level below a certain degree is not going to be a genuine satellite system. So there are ways of filtering out, shielding out those low degrees of elevation because they are not satellite systems. You also want to filter out undesirable noise and energy. There are different antenna implementations and filters that exist to reduce possible noise, either intentional or because you're in an environment where there is noise around it. And then the last thing also that is quite common and has been around already from a technology point of view for 10, 15, 20 years is CRPAs, Controlled Reception Pattern Antennas. These are intelligent multi-element antennas which allow you to do beamforming and null steering in order to use a number of algorithms which are usually proprietary to the vendor's implementation for those antennas, but based on certain weights given to phase, power, direction, you can compensate and try and filter out signals that are actually not from a genuine GNSS source. The combination of all this is the 101 of being able to secure the RF signals that come into your Grandmasters in plural because you want redundancy. This is a quick slide to demonstrate the fact that GNSS has multiple sources and frequencies. You have the different constellations, satellite systems, and you see the different bands in which they operate. Once again, modern Grandmasters will allow you to use multiple bands and multiple systems, and using their own correlation mechanisms will allow you to have better or more accurate timing. Question that comes across quite often is, well, what happens if I've got multiple Grandmasters and I want to use them in parallel? Aren't I going to have some sort of offset? So this is a snapshot that we took some time ago, demonstrating the output, 1 pulse per second output of 2 separate slaves connected to 2 separate Grandmasters, to 2 separate antennas, to 2 separate GNSS sources. And over time, this is over about 100 hours, it demonstrates the peak-to-peak values that you're having in terms of offset between the two different systems. This is just a way to demonstrate that we have a limited offset in terms of nanoseconds between multiple GNSS sources across multiple Grandmasters. This may or may not be an issue, depending on what you design, but it is something that has to be considered today, that using one and only one single source at any point in time may or may not apply, both in the campus LAN environment, in the WAN environment also. You may or may not have the opportunity of distributing PTP across the WAN for multiple reasons. You can have multiple GNSS sources over multiple Grandmasters as a means to not only distribute, but also verify that one of the systems hasn't been tampered. What do we need to do next in terms of protection from a PTP disruption point of view? Well, first things first is any device you have needs a decent, good, great oscillator in there. There is no way around it. You need to understand that PTP is there to provide you and to discipline the oscillator, but you need a good oscillator, which gives you a decent holdover period. That holdover period depends on what you're designing. But when things go south, you want to make sure that that oscillator is in there and will be able to run the system, not only on the Grandmasters, but also on the slaves. Traceable sources. There are flags in PTP that imply that you can have a traceable source and also the time source. Those are enabled when you're locked to a reference such as a GNSS source. That's another way of understanding the state of your PTP. The next two features are becoming more and more common in terms of deployments. We can filter out misconfigured or rogued masters/Grandmasters. AMT, Acceptable Master Table, is a standard 1588, IEEE 1588 PTP feature, which allows you to build whitelists of candidate Grandmasters. You know who is supposed to be a Grandmaster in your network. You can build a whitelist using the clock IDs to say, these are the ones that I will listen to. All others will be discarded and hopefully also logged so you understand what's going on. The other option is Forced Master. It's got different names with different vendors, but the idea is the same. You discard announced messages that come in on ports where you've enabled the Forced Master. That means that a device that is misconfigured or is trying to take over as a master Grandmaster will not be able to do so because you're dropping the announced messages that say, I have a better clock ID, I have a better clock accuracy, clock class, or priority than the current Grandmaster. So using those two features, you have a local way of protecting the switch that has got different PTP devices connected, and you've got a remote way of saying, I also have the whitelist, so that across the entire PTP domain, I have only the authorized/whitelisted clock IDs that I will listen to. Next point is usually the one that people come up with is, what about securing the PTP payload itself? So this slide covers 3 possible ways of doing it. The first one exists in the existing current 1588-2008, also known as PTP v2 release of the standard. It's the Annex K. It has always been an experimental annex with a model that we now understand does not work and is being deprecated in the upcoming release of the new 1588 standard. So I'm not going to go any further into that. What I call 1588 next, because it's still not published yet, will be the version 2.1 of PTP. There is now a security TLV for messages and source integrity checking. There are 2 different modes of operation in there. One where you will not accept anything until you've verified all the messages. The other one where you start accepting messages and you verify on the go. Depending on what you design, you will want to use one or the other. This is not part of the current 2059 specification. Most likely we will revise 2059 to support the next revision 1588 in due course. The third option is something called MaxIK, Media Access Control Security. It's an IEEE standard, 802.1ae, which encrypts the entire transport over Ethernet between a host or a port and a switch or another port. So switch to switch or host to switch, for example. It requires a hardware encryption decryption engine in each device. So there is a hardware upgrade that is required in order to do so. It's not specific to PTP, but PTP would also be transported in that encrypted model. It's starting to gain industry recognition. It is a possible way to address securing the PTP payload. So we have key exchanges. That is usually the hardest bit to handle at the early stages, but then become an automated model. So it does require endpoints to support it too. I want to draw your attention on MaxIK again. There are possible impacts, i.e. effects, on the PTP accuracy. Depending on how a vendor implements MaxIK on the host or on the switch, because of the fact that you have the encrypted payload that goes beyond the normal point at which we would do hardware timestamping at the closest point to the PHY, this introduces possible jitter depending on how the encryption engine is operating, encrypt-decrypt engine. So this is not to say that it does not work. It means that vendors need to know what they're doing when they implement it. Otherwise, you will come up with a secure transport, but you're degrading your PTP performance. Another option here is around IPv6. Now, IPv6 might not be the most popular topic right now because people are still focused on building their networks with the existing infrastructure, trying to get to terms with IPv4 and the systems themselves. But at one point in time, you may end up using IPv6, or in some cases, you've decided to go straight to IPv6 because you've decided, although it might sound like climbing a mountain to start off, it will be easier once you're there and you've got a whole system running on v6. There are different views on this. Point here is that in IPv6, we've got something called link local addresses, LLAs. And these are used to exchange traffic locally within the layer 2 domain, so within the boundaries of a layer 2 domain, okay? And it is commonly used by other protocols. One example here is OSPF v3, which is an interior gateway protocol that is very common in routing environments. The point here is that this is not something that is bespoke or something that is being thought on the side and then has been brought back into it. It's been designed from when v6 was designed, and it's been designed with the idea of having information exchange purely locally. So since we contain all the information within a single layer 2 domain, we can reuse IP addresses. These are the link local addresses. They can be either derived from a MAC address, or they can be something static that you've put in there. So in the example I've got here, I show a Grandmaster using an address called FE80 : 1. And then on the boundary clock it's connected to, it's the : 2, okay? The exact same addresses are used on the other side of the boundary clock in a separate layer 2 domain. That information is shared only within the layer 2 domain. It doesn't go any further, and because we're using link local addresses, we also use a multicast scope, which is designed to stay within the local domain. So it will not go beyond that domain. So in the same way that OSPF does this to exchange between its neighbors for its routing tables, we will be doing this, or we could be doing this for PTP. And this, by the way, already exists and is deployed in some environments. So this is an overview of what you want to secure, how you want to secure it, and the different means that you have. And now I'm going to hand over to Nick to cover the next part.
Okay. Thank you. What we need to look at, as Thomas mentioned, is all links within the chain you build for transferring timer information accurately. And of course, at the bottom end, the PTP stack at your end device needs special attentions as well. And it can improve resilience against security if you, for example, have extensive parameter range checking and limit the possibilities to configure the PTP stack using management messages, thus avoiding some attacker meddling with your configuration on your end device. And as mentioned before, the acceptable master table again is an incremental way to improve resilience while at the same time limit dynamic reconfiguration at the PTP stack. So that's protocol related stuff. And of course, holdover time is very critical because there are some attacks which cannot be prevented but would cause sort of a network failure transient, and then the holdover performance is crucial. And this is done using extended filtering, using sophisticated control loops rather than very simple implementations. Now, what's our enemies? What's our aggressors? So we have a number of attack vectors we need, internal attack vectors we need to look at. First of all, somebody can tamper with announced messages. This guy can pose as a legitimate GM and start taking over the network. It also can cause frequent master election rounds, which effectively sort of inhibits time transfer on a long run. And then, of course, it can tamper with time information itself by sending PTP event messages with wrong or slightly wrong time information. And finally, somebody can launch a denial of service attack by swamping the network with PTP messages, sort of saturating the PTP stack because it has to process thousands and thousands of messages per second, and it can also cause permanent master election rounds. So these are sort of three distinct groups of attacks which we need to look at. So now to the interesting part, which is the proof of concept.
Thanks, Nick. So we've talked about the theory so far. And for those who wonder how this can actually work in the real world, we're going to give you a bit of a flavor on a proof of concept attack that we ran in our lab. So this is a fictitious scenario, of course, where the goal is to plant a rogue grandmaster that will modify the time versus the normal primary reference clock. So that rogue device, we assume, did not follow all the guidelines we talked about on the previous slides. It was either planted there, or it was taken over, or something was misconfigured. Anyhow, a device has been owned, as one likes to say. What does it do, first of all? It will join the network. It will slave itself off the current time, and it will stabilize itself. It has a good oscillator, because we mentioned that having good oscillators is important. First, it listens to and it records the current grandmaster data set. So what's the current priority, clock class, clock accuracy, offset. All the information that is needed is being captured and cloned. Next, what it does, it announced that exact same data set. But in our case, we've decremented a field, the offset scale log variation field, which is decremented by 1. It's a value that usually starts at around 65,000, and depending on the long-term stability of your grandmaster, should decrease over time to stabilize at a certain point. In the BMCA, the best master clock algorithm approach, we know that if we have everything that's identical, somewhere there's got to be a tiebreaker, but further up the stack, if we have an OSLV value that is better than the current grandmaster, according to BMCA, this is the new master. We duplicate everything, the clock ID, the traceable flags, the whole thing. Depending on your PTP stacks, there may or may not be another election. So it may go completely unnoticed. It might, and it's entirely dependent on the PTP stack, as I said, because PTP stack design is not standardized in 1588. It's implementation specific. By changing that value, the OSLV value, we would believe that if it's the exact same set of information, but the value's been improved slightly, we just have long-term better stability of that Grandmaster. So it might go completely unnoticed. What we want to do here then is we want to change the clock rate. In our case, we use 10 ppb as an example because we want it to be slow enough to go unnoticed. You could have used 1 ppb or another value, but for the purpose of our test, we use 10 ppb. All devices will now start to drift with respect to the legit reference clock versus the rogue one, which they're all now taking time from. And the whole point here is that the attacker will then launch his attack, and you understand what we mean here, when he feels is the best moment to cause, we assume, max disruption. So what he has to do is, whilst he's been in, we'll say, cloaking mode so far, when he launches his attack, it doesn't matter if he discloses himself to the world because obviously he's about to attack. So he stops sending his announced messages. That obviously triggers a BMCA because now the legit Grandmaster is going to come back online, or it might go completely unnoticed because in theory only the OSLV changed again. But if he stops sending his messages, there is a high chance that a BMCA will occur. Re-election of the legit GM, and then suddenly there's going to be a jump in the timeline since we've just moved. So based on how PTP stacks are not standardized, it may reset, restart the stack, it may slew the clock. It wasn't designed for that environment. Something might happen, it might crash the stack, who knows? And the behavior of the PTP stack versus the behavior of the application using the timing on top of it may be different also. So the quick lab setup is very simple. We have a GNSS source, we have a Grandmaster, we have a scope because we're measuring 1 PPS, we have the reference network adapter, we have a boundary clock in the middle, and we have a rogue GM. So extremely simple setup with just a couple of devices, and we are going to measure the 1 PPS on the scope from the Grandmaster and the reference NIC, and we're going to compare the results. Nick, back over to you.
Okay, now I shall present you the results, which are quite interesting. What you see here is that's the real world implementation. So that's what actually happens in the devices. That's an ideal measurement, which is the 1 PPS measurement. You see this multicolored edge is the 1 PPS of the Grandmaster, and on this scope you have several measurements on top of each other, so-called envelope mode, and you see the slave is drifting apart onto the left-hand side. And now when we jump back again, you see very quickly in that implementation, second by second, the 1 PPS jumps back and causes, of course, a disruption in this specific timing behavior of this specific slave. And keep in mind what Thomas mentioned is that's one implementation with one specific configuration set. This specific implementation could behave differently if you configure it differently. So you are not even safe if you say, okay, we have one common implementation. Now, if you look at the data the PTP stack is reporting, so that is the input offset using the well-known formula for the 4 timestamps. And what you see here is one erratic message which is filtered out because it's considered an outlier. So the resulting effect when you really query the PTP stack is it's well behaved to a valid Grandmaster. And the interesting thing is the next slide. That's the output if you simply queried the PTP stack of the affected device with this Grandmaster, with the rogue Grandmaster and with the complete attack. And what you see here is quite disappointing. You see nothing because it's not the real world. What happened was on the scope. And when you look at the input data, additionally, you see the rogue Grandmaster and you see it jumps back again, and then all of a sudden you see microseconds, tens of microseconds offset. Okay, now, quick word to the countermeasures before we conclude. What you should do is, first of all, again, prevent unwanted access to your network. And we couldn't reiterate it often enough. Monitor your PTP behavior, message rate, state changes, accuracy, so you can react and can detect attacks. And then provide sufficient level of countermeasures, semi-automatic isolation of affected networks. For example, if you see something is wrong, you can just simply isolate it. Disable PTP traffic, for example, and when you start disabling it, it's important that you hold over performances sufficiently well. We mentioned acceptable master tables, forced master states on all boundary clocks and switch, and as an additional measure, but not as your first line of defense, you may secure PTP messages. Let's conclude. First of all, you should do your homework by securing your network. And please keep in mind, it's not about if, it's about when. It could be a malicious attack. It could be an inadvertent effect because something is misconfigured. And the whole chain is of importance because starting from GNSS signals, antennas, GMs, the whole PTP network and the end devices all have to play together to guarantee reliable and accurate time transfer. Keep in mind, PTP is always a multi-vendor deployment because you have switches, you have Grandmasters, you have slaves. Model likely and unlikely threats, be prepared, and when you model them, you can devise robust means to detect and to mitigate them or even prevent them. So one interesting, as we mentioned, is use as many features PTP offers as part of the standard, and as we mentioned, secure the PTP messages will help you, but is by far not the most effective means to prevent any attacks. Thank you.